Okay, in this video, we are going to discuss about the polyphase circuit, which is the last unit from the motor descriptor, the circuit theory 1. Now, three-phase electric system may be considered as three separate single-phase system, where each phase is displaced with 120 degree or 2 pi by 3 radians, and then the peak of the respective voltages do not occur simultaneously. For example, in this waveform here, we can see that here we have three phase. We are considering this line as one phase, and then again this waveform as another phase, and then this line as your third phase. If we compare the phase angle or the phasor displacement between each phase, let's simply compare between the phase 1 and the phase 2. If you are considering here at this peak here, it is starting at 90 degree. At 90 degree here we have a peak voltage, or let's say the peak amplitude for the phase 1, and then now 180 plus, at 210, now this one will be 210 degree. At this here again you have the peak amplitude. Now between these two peak amplitude, there will be the phase shift or the phase difference of 120 degree. And then similarly, if you compare it with the phase 2 and the phase 3, you'll have again the 120 degree phase difference, which means for the three-phase system, it is the combination of the three single phase where each phase is separated by the 120 degree each. Now in case of the three-phase system, there will be two types of configuration. The first one is star connected, and then the second one is the delta connected. Now in case of the okay, let's discuss one by one. Now this is the representation for the star connected. Now here I have taken some windings or some load here, and then the sequence we're going, it is R, Y and B here, and here we have the voltage, the phase voltage. Now when it talks about the three phase, you'll also come across the term the phase voltage. Okay, here let's write here phase voltage, and then the line voltage. Now these are the two types of voltage that you come across when you talk about the three-phase system. The phase voltage is the, in case of the star connected, it's the voltage which is measured between the one of the phase to the neutral conductor. Now in this case, your V and R is your red phase, R phase voltage, and then again in this case here is the Y phase voltage, and for this one is the B phase voltage. And then for the line voltage, it is the measurement between phase to phase, or we also call it as line to line, phase to phase voltage. Now okay, for this one, if we represent it in the vector form, we can write like this. Here we have the phase voltage V and R here, and then V and Y and VN, and each phase is displaced by 120 degree each. Now for the line voltage, it is measured between this line to this line, or like from this to this, or from this to this, or from here to here. Now in order to find the relationship, now in case of the balanced three-phase system, now when I say about the balance, the connected load in each phase is equal. The connected load of each phase are equal. Now for the balanced system, we can write that the phase voltage, let's say, okay, now that phase voltage can be also represented like this. VNR can be also written as VR, and then your VNY can be also written as uh, VY, and then VNB can be also written as VB. Now in case of the balanced system, if you're talking about this one, if you're talking about this the vector representation of the interconnected three-phase system, we can write that your VR is equal to that voltage, that line voltage at an angle of 0 degree volt. And then for the Y phase, for the Y phase, it can be represented as V, the line voltage at an angle of minus 120 degree voltage. Now here we are taking this R phase as a reference voltage. Now this one is at the 0 degree, and then after that, if you measure from here to here, we have to consider that it's moving in anti-clockwise direction. That's why we are giving it as a negative 120 degree here. And then for the B phase, you can return it as at an angle of plus 120 degree, or you can also return it as V at an angle of minus 240 degree. Now this is the phasor relationship for the balanced three-phase interconnected system. Now the second system is we have a delta connected. Now in case of the delta connected, you will not find the neutral point. Okay, and one important thing from the, okay, now we can also derive the relationship between the line voltage and the phase voltage in case of the star connected. Now in case of the delta connected, we don't have the neutral point here, so we can directly have that your phase voltage will be equal to your line voltage in case of the delta connected system. So in case of delta connected system, this is the representation of the delta connected system, and here you have the vector representation of the delta connected system. And then if we extend this one, if we extend this line and measure the angle between R and Y, you will find it 120. And similarly, if you extend the R and measure the angle between Y and R, you will find angle 120. And then similarly, if you extend the that B phase and measure the angle between R and B and R, you will find 120 degree, which is same as we are writing it here. We are writing like this. Now this is the similar representation that we have. We can derive it from here, that the vector representation of the delta connected, and then we are simplifying and we come to this. And here we are also taking R as a reference voltage. And then similarly, now we can also write the in case of the balance system, we can write the line voltage for the balance system as your VRY will be equal to the line voltage at an angle of 0 degree, and then your VYB will be equal to at an angle of minus 120 degree, is displaced by 120 degree, and then for the BR it will be displaced with minus 240 degree, or we can simply write V at an angle of plus 120 degree volt. Okay,